TIG welder.
Well, yeah.
Yeah.
Well,
Yeah, but that's a good example. What have you seen?
Sorry, I'm trying to think of how to describe it. They have the heat treat and the soldering. They didn't use the soldering in the shoe.
And maybe what would they solder?
They would solder pieces together or use a culture.
Okay, so I can't really identify. You have something in mind?
Well, I had a project in high school where we did the soldering with the stained glass,
Bingo.
like something. So we took like a little piece of metal, we had to use the solder to kind of melt it down onto it to stick together.
You've all seen stained glass. That's a good example. The material that links the pieces, the panes of glass together, is called cane. It used to be a pewter material, a lead-based material. Now it's a non-lead-based pewter material. But either way, if you look to the seams where they build that little armature where the glass fits in, you'll find these big puddles that join the two halves together. Have you ever seen anybody solder wires onto the back of a set of speakers? Ever seen the circuit board in your phone? It's got all these silvery puddles, right? And there's wires that go into the puddles. So if you want to link the current between this wire and this wire, you would do that by soldering them with a puddle of this silver-colored solder. Plumbing. If you got proper plumbing, well, what were you going to say? Did I call on you?
yeah.
Oh, I did. Anybody say plumbing? All right, it was automobile plumbing.
Well, I said pipes.
And you said pipes, plumbing pipes, yeah. If you got proper plumbing in your house, and your plumber wasn't up to speed like whoever it was that plumbed my house, I've got these drips. Wherever the female fitting goes into the male fitting, I've got these drips of solder because there's not really a snug fit between those fittings, and they make them that way so that it's easy to assemble. And then you flood them with that solder. Those types of solder have nothing to do with what we're doing. Those are low temperature soldering examples. They derive their strength from those great big puddles of material. If you think about jewelry, which was your example, you look at the back of a pair of earrings where the post meets the earring, you don't see solder. It seems like it's just a natural joint, right? They just join together with some type of invisible mechanism. But in fact, the solder's there, and it's multiple times, although you can't see it, it's multiple times stronger than the soldering that you're familiar with. And that's because our soldering process causes the high temperature. Our solders go about 800 or 900 degrees higher temperature melting than the low solder, the low temperature solders that you folks were just offering examples. So you don't have to write any of that down yet. No, don't write any of this down yet. I want you to kind of understand the concept. We're going to get into the details in a minute. So if we can kind of see through this piece of metal, and I'm going to join this piece of metal to the other, I have to cause the solder to reach up into the pores of the metal at the point of contact. So they have to reach up into this piece where that flat end sits upon this flat plane, and the solder has to move down into the bottom piece also at that point of contact. So it goes up into the metal and it goes down into the metal. So there's no big puddles hoping to stick the material together like you'll find on a circuit board. Your plumbing, was it your plumbing? Somebody nodded their head when you talked about bad plumbing. Your plumbing, my plumbing, your stained glass windows. So to accomplish that, we have to meet a fairly significant list of expectations. So the first question that I want to ask you is, what might dropping an egg off a 7-story building have to do with high temperature silver solder? What do they have in common? Any idea at all? Dropping an egg off a 7-story building. What can that have in common with high temperature silver solder? Pardon? I'm going to keep a close eye on you. That's scary. Pardon?
The delicacy of it?
No? What do you think? What do you know about about dropping an egg off a 7-story building?
You know how to do it when
What do you know?
project.
Oh, it's going to shatter. What happens the second time?
It's so sad.
15th time?
Shatters.
100th time?
Shatters.
Absolutely predictable. Because there are a number of laws of physics that come into play. And can we violate the laws of physics? No, and the final principle is that two masses can't occupy the same space. So obviously the egg gives way to the side one. So we have all those forces coming to bear on that process. The absolute same thing applies to high temperature silver soldering. If you meet all the expectations, to adhere to the laws of physics, you understand the chemistry, high temperature silver soldering has to work. It has no choice. You eliminate one aspect of the process, one element of the process, it will not work. If you eliminate one detail from my scenario with the egg, it's not going to break. So if we eliminate the 7-story building, it's not going to break. We eliminate the egg, there's nothing to break. We eliminate the sidewalk, then there's just an empty void in the wall. So you have to take very, very careful notes, write down every single detail. You have to understand the details. I'm not showing you how to solder. I'm actually teaching you why soldering does occur. And then you can understand all the principles that define high temperature silver soldering, then you can solder. If I simply showed you how to solder two pieces together, that would be relatively useless for you. I will demonstrate that, by the way, maybe at the end of this night if we have time, or at the start of class next time. I will demonstrate that. But if it were simply to show you how to solder two pieces of material together, that would be useless. Any idea why? You think about the Ford production line, kind of revolutionized manufacturing. All you had to do is teach a guy how to turn nuts onto the right rear tire, right rear wheel. He didn't have to understand how the car worked. He didn't understand any other process required to assemble an automobile, because that one individual only had one job to do this. So he doesn't have to understand anything beyond. You just take that nut, put it on the end of the bolt, and then you turn, and then you torque to a certain specification. All you need to do that. His job was the same every single time another automobile moved in front of him. What's the problem for us? Every single one of you will be attempting to solder pieces together in a way that no one else ever has. Because the relationship between any of your two pieces is unique. Because you created unique forms. So if I showed you two pieces of metal being joined, the way you balance your flame, the way you set your solder will be different. Even though you're also soldering two pieces of metal together, because the size relationship will be different, the angles may be different. There are a number of factors that come into play to make each and every solder joint unique. So you have to understand the process so you can make those adjustments. So, how many of you have ever painted something and it's been exposed to the elements for some length of time? It gets, when you first paint it, it's nice and shiny. And over time, it gets filthy. You wash the surface, when it's perfectly clean, it's no longer shiny. It's dull. How would you make it shiny? Polish it, right? You add some type of polishing agent. So here's what you're doing. Virtually all materials are porous. You all know what porous is, right? So a porous surface is an uneven surface. An uneven surface is, for the most part, a dull surface. So when you polish the surface of that paint that over time has eroded and exposed its pores, literally your polish is contaminating in a positive way or sealing those pores and creating a much smoother surface. A smoother surface is a shinier surface. Is that correct? So imagine when you first wash that painted surface and you dry it and it's dull. And then it rains. It always rains, by the way, if you wash something, right? So in my day, we didn't have this clear coat on our cars. So this is what we experienced when we were washing our automobiles. They came out with paint. If you wanted them to shine, you had to polish them. So they would dirty over the course of the winter. My car maybe over the course of 3 years. Then eventually I would wash it under duress. And then when I would rinse it, it would be perfectly clean and the surface would be dull like we just talked about. And then it always rains after you wash your car. So when it would rain, does anybody have an idea if the water would bead up or form a skin on a dull, clean surface? Does the water bead up or form a skin? Skin. Yeah, it forms a constant, even skin, and that's because the water is able to reach into the pores and form a tension across the surface. So then you dry it, and then you polish it, right? And you seal those pores. On a newly polished surface, if it rains, it beads up, the water beads up. Yeah, in my day, we would take the car for like 4 miles an hour, hit the brakes, and the water would stop. Because it would bead up and it would want to roll off, because it cannot reach into the pores of the material. Now you remember when I was just giving you a general idea of how high temperature silver soldering works, I suggested the solder has to reach up into the pores and down into the pores of the metal. Because those big clumps on the sides that you've seen in other forms of soldering are unacceptable in high temperature silver soldering. So the strength comes from the solder reaching into the pores, which tells us the metal has to be absolutely clean. So you want to write that down. And we'll talk a little bit about clean. So first and foremost, if you don't clean your metal prior to soldering, what do you think the silver solder will do? Can I see one of your packets? Do you have any idea what this wire has in common with water at 31 degrees? Yeah, it's a solid. Right. This is just a liquid that's frozen. It has a much higher freeze temperature or melting temperature than water. But essentially, we're going to heat this material until it's transformed into its liquid state. And then, in that liquid state, it's able to reach up and down into the pores. This is A. You all see A? You all see A? Be careful, look at A. You all see B. Which one of these is clean enough for soldering, A or B? Pardon? How many of you vote for A? Good voting. How many of you vote for B? How many of you have another answer? Pardon? Neither. Yeah, this metal will not accept solder any more readily than this metal will. Because it's not a matter of how dirty it is, it's simply that there's dirt. And the dirt seals the pores. If the pores are sealed, solder won't adhere. So, why is this metal dirty? It looks pretty clean. This is what we call, well not now because it's been cut. Let me find another piece. That even looks cleaner, right? It's also filled. This is called virgin metal. It's called that because that's what you call metal. It comes from the manufacturer. It hasn't been affected yet. So this arrived a few months ago in a cardboard box. We pulled it out a few weeks ago, chopped it up into these little pieces, stacked it up into the box. I just pulled the piece out to show you folks. Tell me why this piece of metal is too filthy for soldering. It certainly looks good. Yeah, yeah. You know, that's how they catch you when you steal your neighbor's flower pot from the porch. From your fingerprint. Because everything we touch leaves a little bit of our body oil on the surface, right? So obviously oil fills those pores. There's microdust in the atmosphere. Fills those pores. This is oxidation. This is very heavy oxidation on this metal. It's actually the result of spontaneous oxidation, which we'll talk about later. But oxidation is constantly occurring when the atmosphere interacts with metal. Anybody give me an example, put a name to some form of oxidation? Anybody know what iron oxidation looks like? What it's called? It's rust. Yeah. So you obviously have a garage that's too narrow to fit your car. So when you're pulling in, you scrape that fender, and then it reveals this beautiful silver-colored metal, right? Right? It's beautiful. And then 2 days later, it's been a little bit humid, it rained a couple times, and it starts to turn that orange color. That's iron oxide. So what's happening with oxidation is the metal on the surface actually is combining with the oxygen in the atmosphere, and it's really being accelerated by other chemistry that exists, particularly sulfur. So that we form a new compound on the surface. So on the surface of this metal is a heavy coating of copper oxide. There's a fine coating of copper oxide on this metal. As soon as it comes, virgin from the factory, as soon as it comes out of that machine and they wash it, it starts to oxidize. Because it's just a natural condition of metal being exposed to the atmosphere. Anybody give me an example of copper oxide? Tell me what color it is. What color? I'll give you a hint. Right? It's green. Tell me something that's got a heavy green copper oxidation. Statue of Liberty. Right? I think it was like $6 million some years back. They spent stripping it and restoring it to its original bronze tone. And it's actually is a color very similar to this. Because the bronze is an alloy of copper, mostly copper. They may never do it again. Because I'm telling you, so within months it was going green again because the atmosphere is so contaminated up in that part of the country. So, these metals have to be cleaned. You can always assume that your metal is dirty, regardless of how it looks. So before every solder joint, you have to clean your metal. After every solder joint, and you'll find out why, we have to clean our metal. Sometimes that's the same cleaning process, right? Because you're going to solder joint A to B. Now the metal's dirty, you clean it, which is after A and B, right before B and C, right? But it has to be cleaned just prior to. If it sits in your box, you cleaned it, you ran out of time, it sits in your box for 3 or 4 days or a week, when you come back in, you have to clean it again. Because again, oxidation begins almost instantaneously. And even though you don't see it, it's filling up those pores. Okay, so we've cleaned this metal. And we've met one of the primary conditions. How many of you guys who know who Mr. Wizard is? They've forgotten Mr. Wizard. That's because they all have the old mind. Science guy. Poor substitute. Poor substitute. But I'll tell you honestly, I was a little kid. The first time I saw this experiment, sitting on the living room floor, which was rough, in front of a little black and white TV, and I saw Mr. Wizard do this experiment. It looked like this. And it was fascinating, like magic. What Mr. Wizard did. Did I tell you folks? I got you cups.
Oh.
Yeah, I got you cups. Right? And there's a water cooler. So whenever you get thirsty, just help yourself.
I'm like genuinely excited about that.
You what?
I'm genuinely excited about that.
I'll tell you what, I live by it. My mouth dries out and then I stumble on words. So what Mr. Wizard did is he took 2 small window panes, something like 6 by 9 inches each. He put a rubber band around the 2 window panes so they were held tightly together. He supported them vertically in what might look like a baking pan. Then he put about 1 inch of water into that baking pan, which means the bottom of the glass was submerged 1 inch in the pan. Any idea what the result of that experiment was? Yes.
It wicked up.
It went up. You're suggesting the water went up
Yes.
Higher than this level.
Yes.
Now, doesn't that seem insane? Because we know the water seeks its lowest point. This is gravity. Anybody ever seen water run uphill? Would be insane. But she's absolutely right. Because there is a force greater than gravity itself coming into play here. Anybody know the name of that force?
No.
What was it? Possibly. But another force that might be coming into play here. We're defying the laws of physics here with another law. Yes?
Either adhesion or cohesion.
Pardon?
Adhesion or cohesion, it's the force that draws water next to other objects.
Yeah, but there's another name for the particular force that will drive it in defiance of gravity. Begins with a C. What does a baseball player wear on his head when he's out in the field? There we go. Capillary action. So we have a tension that's drawing that water to a level higher than the base amount. Where do we want our solder to travel if we're going to have a strong joint? Up and down between the two pieces of metal. So what does that tell you about the relationship between those two pieces of metal? It has to be tight. So your seam here has to be tight because you can't put the solder between the two pieces of metal because they're little barrels. And I'll tell you why I got wire rather than anything thinner. But even anything thinner, if you put it between these two pieces, when it would melt, those pieces would shift. And I have to tell you, in small sculpture and jewelry making, you can't have your elements shift. Now, in the pieces you're making that shifts a little bit, it's probably okay because you're dealing with a pretty broad dynamic. But if you're trying to assemble like 6 or 7 elements into a fabricated ring, if one of them slips, nothing else fits. So the metal has to be assembled tightly prior to putting any solder near the joint. So how do I get the solder in there?